Oh, class. Okay, so we're going to talk about the magnetic force on a wire that is carrying a current. So let's say we have a wire here that has a length L, and it carries a current I. And let's say there's a magnetic field here in the presence of this wire that makes an angle theta with respect to the wire. So right now we're considering just a straight wire, simplest case. Now, this current means that there are moving charges. And so if the charges are moving, if we have moving charges in the presence of a magnetic field, there's going to be a force on those charges. Now, these charges can't leave the conductor. It would take a large force to actually do that. And so the force on the charges is going to show up as a force on the wire itself. And so we know that for an actual, like a conductor, the moving charges are actually negative charges moving in the opposite direction of the current, but that's actually kind of irrelevant. We can say that, just to make our lives easier, let's say that the current consists of positive charges moving with the drift velocity. So what's actually going on is we have negative charges in this conductor, and they have a tendency to drift to the left. The electrons have a tendency to drift to the left with this very low drift velocity. But the result would be the same as if we had a bunch of positive charges just moving straight down the wire in a nice orderly fashion. So to make our lives easier, we will treat that as our current. Okay. So the force on the wire, in a sense, is very simple to write down. The force on a single charge is just q v sine of theta, or in this case, vd, the drift velocity. That's the force on a single charge. So all we have to do is multiply by the number of charges, and we're done. What is this number of charges, though? Let's say our wire has a cross-section area A. Now, the current, now it's defined as dq over dt, but let's, we're treating this as a nice orderly current where everything's moving at a constant velocity vd. And so, in that case, we can replace the d's with deltas. And so, the charge, so let's look at this end of the wire. And let's say delta t is the time it takes for a charge moving at the drift velocity, starting at one end across the wire and exit the other end. So, from distance is speed times time, we have L is equal to Vd times delta t. And every charge that starts out in this wire, if we define delta t in this way, if they're all moving at the constant speed down the wire, then every charge that's in this wire is going to make it up past that end. Where if a charge was not in this wire, of length L, like if we had a charge here, it would travel a distance L, which would make it about here, but it wouldn't cross through the end. And so delta Q, let's rewrite our current here, delta Q would just be N times Q. So N is the number of charges that are, say, in this wire, and or this segment of wire of length L. Q is the charge on a single carrier. And we divide by delta t, which is L over the drift velocity. And so we see here nq times the drift velocity that's equal to I times L. We just multiply by L. And so the force on this wire is ILB sine of theta, where this is, of course, is just the magnitude of the force. Now, what is the direction? In this case, put your fingers in the direction of velocity, curl towards the magnetic field. It's coming out of the board. And so we can write this as a cross product. We just have to be careful to get this right. And so what we do is let's define a vector L. So let's make L a vector. And L points in the direction of the wire. So the magnitude of L is the length of the wire. And it points in the direction of the current. And so we know positive charges moving in this direction. From the right-hand rule, force is out of the board. And so we can write this, the force. Well, here, let's do this first. Let's look at L cross B. So we define this vector L to be in the direction of the current. So L cross B, the magnitude of L cross B is going to be LB sine of theta. And so what we have here for our force, and the direction is going to be right as well because L points in the direction of current. Curl your fingers in the magnetic direction of the magnetic field. The force is out of the board. So we can write the force on a wire. I'm going to write it both ways. So we have ILB sine of theta. That's just the magnitude of the force. If you want to write it as a vector, a little more compact there, and it also gives the direction. Although, carrying out the mathematical cross product using determinants, it's much easier just to use a right-hand rule. But that's a more compact way of writing it. All right, so that's the magnetic force on a straight wire. Now, what if we don't have a straight wire? Or what if the magnetic field wasn't constant? So if we had just a more general case, say we had a wire that looks like this. And the magnetic field, just pick, say we're in a constant magnetic field, just for the sake of the drawing. Does not require a constant magnetic field because we're going to break our wire up into pieces. So let's look at this piece here. If we make it small enough, so say the current is this way, let's call this segment of wire ds. And so df would be the force on that segment of the wire. That would be I ds cross B. And so if you wanted to find, so again, it's just just looking at a small piece, and then to find the force, we would integrate this expression. Now again, this is complicated because we are dealing with vectors. In this case, it was simple because the wire is in a plane. You can imagine a more complicated wire, though, that came out of the board, for instance. Because if we take this cross product, ds cross b, in this case, ds cross b is out of the board. Now, the magnitude of ds cross b will depend where you are on the wire because it involves the angle between the wire and the magnetic field, and that's obviously changing here. But at least it's always going to be pointing in the z direction. So if you had something more complicated, say you had like a helix, like coming out of the board, this expression is still good, but again, that would be fairly difficult to actually you know, integrate something like that, because the direction would of the force can change depending on where you are, not just the magnitude over any segment. So these calculations can become reasonably complicated. But you know, force on a wire. This is actually a very important topic, but we're going to save that for another video. So we'll just keep this one short and just leave it here for now.